Today I'm talking about the energy and the process our cells and other animal cells go through to provide themselves with power. Cellular respiration is how we derive energy from the food that we eat, specifically from glucose, since most of what we eat ends up as glucose. Here's the chemical formula for one molecule of glucose. In order to turn this glucose into energy, we're going to need to add some oxygen, 6 molecules of it to be exact. Through cellular respiration, we're going to turn that glucose and oxygen into 6 molecules of CO2, 6 molecules of water, and some energy that we can use for doing all of our push-ups. So that's all well and good, but here's the thing. We can't just use that energy to run a marathon or something. First, our bodies have to turn that energy into a really specific form of stored energy called ATP, or adenosine triphosphate. You've heard me talk about this before. People often refer to ATP as the currency of biological energy. Think of it as an American dollar. It's what you need to do business in the US. You can't just walk into a Best Buy with a handful of Chinese yen or Indian rupees and expect to be able to buy anything with them, even though they're technically our money. Same goes with energy. In order to be able to use it, our cells need energy to be transferred into adenosine triphosphate to be able to grow, move, create electrical impulses in our nerves and brains, everything. A while back, for instance, we talked about how cells use ATP to transport some kinds of materials in and out of its membranes. To jog your memory about that, you can watch that episode right here. Now, before we see how ATP is actually put together, let's look at how cells can cash in on the energy that's stashed in there. Well, adenosine triphosphate is made up of a nitrogenous base called adenine with a sugar called ribose and 3 phosphate groups attached to it. Now, one thing you need to know about these 3 phosphate groups is that they are super uncomfortable sitting together in a row like that, like 3 kids on a bus who hate each other all sharing the same seat. So because the phosphate groups are such terrible company for each other, ATP is able to do this nifty trick where it shoots one of the phosphate groups off the end of the seat, creating ADP, or adenosine diphosphate, because now there are just 2 kids sitting on the bus seat. In this reaction, when the 3rd jerk kid is kicked off the seat, energy is released. And since there are a lot of water molecules just floating around nearby, an OH pairing, that's called a hydroxide, from one of the H2Os comes over and takes the place of that 3rd phosphate group, and everybody is much happier. By the way, when you use water to break down a compound like this, it's called hydrolysis, hydro from water and lysis from the Greek word for separate. So now that you know how ATP is spent, let's see how it is minted nice and new by cellular respiration. Like I said, it all starts with oxygen and glucose. In fact, textbooks make a point of saying that through cellular respiration, 1 molecule of glucose can yield a bit of heat and 38 molecules of ATP. Now it's worth noting that this number is kind of a best case scenario. Usually it's more like 29 or 30 ATPs, but whatever. People are still studying this stuff, so let's stick with that number, 38. Now cellular respiration isn't something that just happens all at once. Glucose is transformed into ATPs over 3 separate stages: glycolysis, the Krebs cycle, and the electron transport chain. Traditionally, these stages are described as coming one after the other, but really everything in the cell is kind of happening all at the same time.
Everyone has been to a mechanic before. Likely, you took your car to him or her either for regular maintenance or because something went wrong. Because of their understanding of those fickle, ubiquitous machines we all use, they were probably able to diagnose the problem relatively quickly and get you back on the road in a few days at most. Far fewer people have ever been to a biomechanic, or even know what one is. In this lesson, we will explore what exactly the field of biomechanics is and look at its applications and uses in the 21st century. Biomechanics is the study of how the systems and structures of biological organisms, from the smallest plants to the largest animals, react to various forces and external stimuli. In humans, biomechanics often refers to the study of how the skeletal and musculature systems work under different conditions. In biomechanics more generally, scientists often try to apply physics and other mathematically based forms of analysis to discover the limits and capabilities of biological systems. In a way, biomechanics has been around since the inquiring ancient Greek and Roman minds began dissecting animals and vivisecting humans to discover the inner systems of our bodies. Many of the great philosophers and scientists of our past tried their hand at some form of biomechanics, from Aristotle, who wrote on the motion of animals in the 4th century BC, to Leonardo da Vinci, who studied human muscle and joint function in 15th century Italy. In the 19th century, scores of Europeans were incredibly fascinated, for some reason, with the gait of horses and extensively studied the biomechanics of a horse's galloping motion. Today, rather than a field that scientists and philosophers dabble in, biomechanics is its own branch of human and biological science, with entire departments in hospitals and universities devoted to the subject's study. Since biomechanics is the study of human movement and interaction with the environment, the field has myriad applications in daily life and touches on many different sciences. Let's look at a few examples of the areas in which biomechanics is most commonly used. Biomechanics is certainly popular right now in sports and athletics. Sports teams and athletes themselves often hire entire teams to study the movements and forces inherent in the various regular motions and important actions during the playing of a sport. A good example of this is the swinging of a baseball bat or golf club. These are both motions that contort the human body in strange and irregular ways. Teams and/or individual athletes often hire scientists and therapists well versed in biomechanics to study an athlete's motion, often using slow motion cameras to study the angles and forces that go into each action. At the highest levels, figuring out a way to squeeze that extra little bit of power out of a baseball player's swing can be the difference between a pop fly and a home run. The principles of biomechanics don't just matter for large organisms like humans. They're applicable on the smallest scale as well. Indeed, today's scientists are using biomechanics to study animal, plant, and human tissues and materials and discover their most basic properties.
Has anyone ever told you, "Stand up straight," or scolded you for slouching at a family dinner? Comments like that might be annoying, but they're not wrong. Your posture, the way you hold your body when you're sitting or standing, is the foundation for every movement your body makes, and can determine how well your body adapts to the stresses on it. These stresses can be things like carrying weight or sitting in an awkward position, and the big one we all experience all day, every day: gravity. If your posture isn't optimal, your muscles have to work harder to keep you upright and balanced. Some muscles will become tight and inflexible. Others will be inhibited. Over time, these dysfunctional adaptations impair your body's ability to deal with the forces on it. Poor posture inflicts extra wear and tear on your joints and ligaments, increases the likelihood of accidents, and makes some organs, like your lungs, less efficient. Researchers have linked poor posture to scoliosis, tension headaches, and back pain, though it isn't the exclusive cause of any of them. Posture can even influence your emotional state and your sensitivity to pain. So there are a lot of reasons to aim for good posture. But it's getting harder these days. Sitting in an awkward position for a long time can promote poor posture, and so can using computers or mobile devices, which encourage you to look downward. Many studies suggest that, on average, posture is getting worse. So what does good posture look like? When you look at the spine from the front or the back, all 33 vertebrae should appear stacked in a straight line. From the side, the spine should have 3 curves, one at your neck, one at your shoulders, and one at the small of your back. You aren't born with this S-shaped spine. Babies' spines just have one curve, like a C. The other curves usually develop by 12 to 18 months, as the muscles strengthen. These curves help us stay upright and absorb some of the stress from activities like walking and jumping. If they are aligned properly, when you're standing up, you should be able to draw a straight line from a point just in front of your shoulders to behind your hip, to the front of your knee, to a few inches in front of your ankle. This keeps your center of gravity directly over your base of support, which allows you to move efficiently with the least amount of fatigue and muscle strain. If you're sitting, your neck should be vertical, not tilted forward. Your shoulders should be relaxed, with your arms close to your trunk. Your knees should be at a right angle, with your feet flat on the floor. But what if your posture isn't that great? Try redesigning your environment. Adjust your screen so it's at or slightly below eye level. Make sure all parts of your body, like your elbows and wrists, are supported, using ergonomic aids if you need to. Try sleeping on your side with your neck supported and with a pillow between your legs. Wear shoes with low heels and good arch support, and use a headset for phone calls. It's also not enough to just have good posture. Keeping your muscles and joints moving is extremely important. In fact, being stationary for long periods with good posture can be worse than regular movement with bad posture. When you do move, move smartly. Keep anything you're carrying close to your body. Backpacks should be in contact with your back, carried symmetrically. If you sit a lot, get up and move around on occasion. And be sure to exercise. Using your muscles will keep them strong enough to support you effectively, on top of all the other benefits to your joints, bones, brain, and heart. And if you're really worried, check with a physical therapist. Because yes, you really should stand up straight.
Hi, I'm Dr. Mike Evans, and today we're talking about the importance of intensity in physical activity. The stuff that gets your heart pumping. To meet Canada's physical activity guidelines, you need to do at least 150 minutes weekly of something called MVPA. So MVPA stands for moderate to vigorous physical activity. So why is this important? Well, I guess in our lives we want to invest in simple actions that improve many things. Exercise does this, from reducing heart disease or cancer to improving mental health to simply improving the quality of our lives. Now, I often get asked, what is the best exercise? And my number one answer is definitely the one you'll do. But my second answer is, when possible, do an exercise that requires more effort or that is higher intensity. The higher the intensity, the healthier the results. Why? Well, research has shown that higher intensity activities are more effective than lower intensity activities at improving our health, especially when it comes to the important stuff like reducing your risk for heart disease. But what is intensity? Well, I think intensity can be thought of as how hard a person works to do a specific activity. It's important to remember that no two people are the same, so the intensity of different forms of physical activity varies between people and depends on someone's previous exercise experience and their level of fitness. If you're inactive, any amount of physical activity can provide some health benefits. So it's best to start with smaller amounts of activity and gradually increase duration, frequency, and intensity. So how do we measure intensity? Well, we use something called a MET. So that's a metabolic equivalent. So at the high end, running might be an 8, jogging a 5, and at the bottom would be resting or watching TV, which would be anything less than 1.5. Moderate intensity physical activity, which measures 3 to 6 METs, requires effort and noticeably accelerates your heart rate. So for example, walking. Depending on your speed, the MET could range from 2.3 to 3.6. Yard work could be a 6. Housework could be 3 to 3.5, and so on. Vigorous intensity physical activity, which measures more than 6 METs, requires a large amount of effort and causes rapid breathing and a substantial increase in your heart rate. Think of sports or shoveling heavy snow. It's difficult to sustain vigorous activity for a long time. One way to think about this is to reflect on the research on athletes. So for example, cycling really hard for 30 to 60 seconds and then relaxing for the same amount of time and then repeating what we call interval training has been shown to improve performance in a shorter amount of time. The same can be true for the average person. Incorporating short periods of increased intensity into your routine can improve your fitness and decrease your risk of a long list of health complications. Still a little unclear? Let's make it even simpler. If an activity doesn't cause changes in your breathing patterns or make you sweat, then you're probably getting a low intensity workout. If you can hold a conversation but still feel out of breath, you're probably in the moderate range. If you can't talk to your neighbor or sing out loud, you're probably in the vigorous range. If you can do moderate to vigorous activity at least 150 minutes per week, you're meeting the target. So go for a brisk walk, grab a dance partner, a garden hoe, or even a vacuum cleaner and get ready. Get set and up and go.